after having been out from academia for 6-7 years, I came back about 2 years ago and began to wonder, okay, so what are potentially the very important problems on which one would like to devote its energy? And one of the fascinating problems for me has always been issues of perception, classification. Always tried to work in this area, worked on wavelet, thought I would be able to apply it to classification. It didn't work so well. Worked on sparse representation, matching pursuits. My goal again was to try to work on classification. It didn't work so well. So I have yet maybe another approach. And again, I hope it's going to work, but we'll see whether it will or not. Now, how is this relating to latent variable analysis, since this is the topic of the talk? So the main issue I'll be looking at today is to try to understand whether there are ways to define generic approaches and metrics for classification. Now, in what sense is that related to latent variable analysis? Is that the main issue and difficulties is that signals are deformed by completely unknown deformation operators that carry a lot of information about the signals. So there are very classical examples in low level. For example, when you have a video, you have movements. The deformation is related to movements, and movements give you information about objects in the scene. If you think of stereo images, two images are deformed, one relatively to the other one, because of the variation of depths in the scene. Same thing if you have a texture on a 3D shape, it's going to be deformed in relation to the 3D information. These are standard low-level examples. But then you have much more sophisticated, I would say, high-level example. If you look, for example, you want to do character recognition, then the characters, if it's handwritten characters, are completely deformed, and this deformation is written to the writing style, and you can identify someone just based on the way the person is writing. Same thing about speech recognition. Depending upon the gender, the speech is going to be deformed. You can recognize gender, or you can recognize the person. Musical score, well, you have the score and then you have the interpretation. The interpretation is the most interesting things when you go to a concert. So all these things are much, much more complicated deformation operators. And one of the core issues is to try to understand the natures of these, try to understand how to estimate them, or at least understand them. Now, you can view these deformation as not variable, but latent operators. They are there. You need to identify them, and they are very, very complex. If you think of the problem of classification, it requires to estimate in some sense the deformation amplitude. Why? If you take, for example, a digit, a 2, you may deform it slightly, it will remain a 2, and at one point you will deform it so much that it will be a 3. Okay, so there is a transition from 2 to 3, and the transition is a continuous function of this deformation, and knowing how far along you are is fundamental to be able to say whether it's still a 2 or whether it's a new digit. And the estimation of this deformation, in some sense, comes as a byproduct of that, and therefore these latent variable or operators. Now, if you think of the problem from the point of view of classification, really what's the major difficulty in classification is to find an appropriate metric to compare signals. Now, what does that mean? It means that if you have two signals, f and g, which are in the same class here, then the distance between these two signals should be small, and if the two signals belongs to two different classes, the distance between the two signals should be big. Now, if someone gives you this distance, then the problem of classification is relatively simple. Whether it is supervised or non-supervised classification, basically you are going to develop some kind of optimization based on this distance to find out whether a signal belongs to a certain class or doesn't belong to a certain class. But really the learning will all be about trying to understand what's the nature of this distance for the particular classification problem that you have. And therefore, the issue is how to learn the distance, basically what kind of class of distance you will be looking at. mean, you need to identify a distance. Are you going to look at any class of distance or some particular class? And an issue is, how does it relate to deformations? We've seen that deformation is key to understand the behavior, for example, of writing. Second question is, if you have data, how are you going to learn these distances? So everything will be more or less related to this issue of distance and how it relates to classification, to deformation. Okay, there is a low-dimensional framework in which all this is, let's say, relatively well formalized. The low-dimensional framework is the following. Suppose you have a signal which may be a huge signal, belongs to a very high-dimensional space. Hopefully, if you're lucky, the signals you are going to look at do not belong anywhere to this huge dimensional space, but to a relatively low-dimensional manifold. Take this example of a mouse with different expression. All these small images, which are still includes many pixels, will in fact belong to a relatively low-dimensional manifold, and as the image is deformed, you are going to move along this manifold. Now, if you have to quantify the deformation to go from one to the other, one very natural way is to compute the geodesic on the surface to go from that point to that point, and the length of the geodesic basically is going to give you the deformation amplitude. Okay? And the same kind of thing will happen in a database of digits like that which are deformed. You'd like to express, clearly these digits are relatively simple image, belongs to a low-dimensional manifold. You'd like to identify the manifold and identify the geodesic. So the core issue is this one. Find the manifold where the signal belongs and find the geodesic to define the distance between elements of this manifold. Now, the problem is that it doesn't work for real images. It doesn't work for real audio signals and so on. Why? Because signals are much, much more complex, and they don't belong to low-dimensional manifold. If you take these three images, okay, you need about a hundredth of a second to realize that there are two textures which are identical and one which is different. Now, these two textures are realization of Gaussian white noise, so it lives absolutely everywhere in the space, and still you are able to very quickly identify the fact that these two realizations are identical. So they don't belong to low-dimensional manifold, and still you can do it. Now, if you take a real images, these belongs to now standard classification databases in vision. Clearly, these are very complex signals. They have all kinds of deformation, fur, textures, and so on. You won't be able to reduce them with few parameters. Other things, there is this idea that you are going to deform one image into another one. Well, these two textures are identical, but you can't deform one white noise into another white noise. So the notion of deformation here gets much more complicated, although visually they still are identical. Third problem which happens is that now that you don't anymore belong to a low-dimensional manifold, you live everywhere in the space. And if you live anywhere in the space which is very large, how are you going to be able to do estimation? Because you need some form of dimensional reduction to be able to estimate relatively few parameters from the limited number of data that you have. These are the questions which are arising. Now, these questions, people in computer vision know them very well. They know them very well. They've been trying to develop techniques to go around that. And one of the key issues, of course, is the issue of dimensionality reduction. How can you reduce dimensionality to be able to do your recognition task? Now, there is one thing which is very important also, is the fact that, as I said, two elements of the same class should have a small distance. Now, it happens that when you have an object, you translate your object. Normally, it's the same object, okay? If you rotate it slightly, it stays the same object. If you move it, it's going to scale over the image. It stays the same object. So you would like to have distances which are invariant relatively to these deformations which maintain an object within the class, okay? And then people have been trying to develop tools to do that. Wavelet coefficients, they build histograms of wavelet coefficients so that the representation gets invariant to translation. They are very nice idea, bags of features sift. And there are these deep learning neural network which also gets very good results for classification. state of the art of computer vision has very much evolved. About 10 years ago, 15 years ago, nothing was working in classification. Now you really have very, very nice results in classification out of these techniques. The only problem is that these are not so well understood. I mean, each developer of an algorithm has its own intuition, but it's very hard to really, from the outside, understand what are these things doing. A key issue which comes out of all these things is the fact that people have realized you absolutely need the high frequencies, but you need to build invariant. So the question is, how can you build invariants from high frequencies and indeed measure the deformations from these high frequencies for performing the discrimination? Now, there is just a point I'd like to make, is that there is another field where these issues of invariant are absolutely key and have been studied since the early 60s in depth, is in quantum physics. In quantum physics, all quantum field theory has been reconstructed by basically saying, if you know the symmetries, in other words, the invariant of your Lagrangian, then you specify some of the property of the Lagrangian of the system, and it entirely defines the interaction between particles. And that's the basic of it in quantum field theory. And if you look at the system which represents, the configuration which represents the system, the configuration is going to evolve along multiple paths, not just one path as in classical physics. Now, these ideas, I mention it because you'll see that in some sense will be naturally led in a direction which is somewhat related to these ideas. Okay, so let me define my wish list. What I want is to define a metric to be able to do classification. And I would like this metric to be relatively simple in the sense that I want to have define a mapping of my function so that the metric is simply an L2 norm over the mapping of the function f and g, so phi of f minus phi of g. Okay, as a fundamental property, the classes are going to be invariant to certain groups of operators, such as rigid, translation, rotation, scalings. So if the function belongs to the class, the translated function, for example, belongs to the class, therefore the distance should be 0 between the function and its translation. What that implies is that the representation here has to be invariant to translation. Okay. This is easy, Fourier transform will do it. But I want something much more. As I said, I want to be able to measure deformation. So now, if I have a non-rigid translation, a deformation, think of it as an elastic deformation. Now, tau depends upon x, so it can stretch the signal. Okay? What I would like is that the distance give me an amplitude of the deformation of the elastic component, therefore the gradient of the deformation. So I would like that the distance should be of the order of the deformation. Third thing, I'd like to be able to deal with processes, okay? Be able to compare stationary processes. So if I have such a distance, I can look at the expected value. I'd like, out of that, to define a metric over processes, stationary processes, to be able to attack the issue of textures. Okay, so this will be basically the program. First of all, I'll explain why Fourier and wavelet don't work. And through this understanding of why these don't work to define such a metric, we'll learn a little bit about the kind of properties we would like to do. I'm going to present a way to build such a distance through what I call here an invariant scattering. And you'll see it's very much related to neural network, deep neural networks. We'll look at the mathematical property of the resulting metric, and we'll look at application in particular on stationary processes. It's very interesting on stationary processes because basically the only thing that exists right now to characterize a stationary process is the power spectrum. And we'll see that we have some kind of nonlinear power spectrum coming out of such an approach. I will then go into the application of classification, and I'll present an algorithm which is O of n, both for learning and for doing the classification. So it's extremely fast, and I'll show results on patterns like digit recognition textures. And very quickly, I'll show how all these things relate and can extend to any group of deformations. So let me begin to try to understand the issue to see how
how things go if you use a Fourier transform. Fourier transform is very natural. We have here an elastic deformation, which is basically a translation, but tau depends upon x. And it's very natural because if you have a pure translation, so tau is a constant, then the Fourier transform, you just have a phase change. So the modulus of the Fourier transform doesn't change, okay? And if it doesn't change, that means you have an invariant representation. That's exactly what you want to have. So Fourier transform is perfect in the sense that if you translate, you have your invariant representation. Now, why the Fourier transform is never used in that kind of application? Why? Very simply because it's absolutely not stable to deformation. Suppose you have a deformation. So tau is not a constant. Locally, suppose that tau is basically affine. You do a Taylor series. Locally, it's a constant plus an affine component. Suppose you take a simple Gabor function, so a Gaussian modulated by a sine wave. You deform your function. So the Gaussian is going to be deformed, but that's okay. It will look still more or less like a Gaussian. But now take your frequency modulation here. It's still going to be a frequency modulation, but because of the affine component, the frequency is going to be shifted. So if you now look at the distance between the deformed signal in the Fourier domain and the original signal, because you had a shift of the frequency and the shift is proportional to the amplitude of the frequency, the distance is not going to be proportional to grad of tau, but to grad of tau multiplied by the frequency. What does that mean? That means if you have very high frequencies, even if you make a very small deformation, suddenly the distance is going to be very large. So basically, high frequency are unstable to deformations. Okay, so what did we see? We see that fundamentally the problem is related to the fact that locally you have some kind of scaling deformation. So scaling deformation, for the one who've been working around wavelets, immediately tilt, you think, okay, so why not using a wavelet transform? Because that's basically the idea. You're going to scale your signal or your wavelet. So let me quickly remind, the idea of a wavelet transform is you're going to take your signal and you're going to filter it with wavelets, which are obtained by taking elementary mother wavelets, which are the psi-k, that I'm going to dilate by 2 to the j. In one dimension, you have one wavelet. The condition you need basically is to take your Fourier axis, and the wavelet is going to be like a bandpass filter, and it's going to be dilated. And you want to cover the frequency axis with all your wavelets to have basically a complete representation. Now, in 2 dimensions, you want several wavelets. These corresponds, let's say, to wavelets having different spatial orientations. And these wavelets are scaled like that, and you want to cover the whole frequency axis that way. Okay? And that's the condition to cover the frequency axis, and then you have something which is basically complete and stable. And I will suppose it's contractive here. Okay, so what's happening now if you take a signal and you deform it, translate, deform? Basically, you see it here. In blue, you have your signal. In red, you have the translated signal a bit deformed. Here you have the wavelet transform. The wavelet transform is a convolution with a wavelet, and therefore you are going, if the scale is large, you are going to regularize the signal, and you get now this much more regular blue signal. The red is just basically translated and slightly deformed, and the distance between the two is going to be small, is 2 to the j is big. And that's what it says here. Basically the distance, if the scale is large relatively to the translation, the first parameter, which is the translation component, is going to be small. And the second source of error is due to the deformation, and you get exactly what you wanted, basically the gradient of tau. Okay, what's the problem? The problem is, what you need is this term to be small. If you translate the signal, basically the wavelet transform is going to translate, but you say, well, it's okay if the wavelet is very big because it's going to be nearly constant. Okay. Now, what does that require? That requires that the translation is small, so basically it will, relatively to the scale, it requires to use very large scales. And there came this idea of coarse-to-fine algorithms. The idea was the following, and many of us worked around these things, and we hope that would be a way to attack computer vision problem. Basically, you are going to begin at very big scale. At the beginning, because they are nearly invariant to translation, you'll have an idea of what's going to happen, and then you'll refine this idea by going to finer scale, finer scale, finer scale. Now, this strategy is basically a failure. It's basically a failure because when you begin at very coarse scale, basically you get rid of all high frequencies. And you can make huge mistake because you remove most of the information, all the fine details. And you make a big mistake, and then you refine your big mistake, and you make other mistakes and so on, and you are completely lost. Okay? One of the things that people have realized in vision is that recognition is based on high frequencies. You can get rid of the low frequency, you recognize everything. You get rid of the high frequency, you are lost. Okay? So it doesn't work because of that. The key question is therefore, again, how can we build invariants from the high frequencies given the fact that the high frequencies look unstable or are not translation invariant? And one way to think about it is to say, okay, the problem I had with my wavelet high frequencies is that they were translating. To have something which is translation invariant, basically the only function which is translation invariant is the constant. So what you would like is to take your high frequencies and to map them back into low frequencies. Not destroy them, but map them within low frequencies. Okay, let's look at this issue. There is one simple way to take a high frequency signal and to map it to low frequency is to just use a modulus. Basically, it will perform the kind of demodulation. I'm going here to use wavelets which are complex functions. So think of them as, let's say, a Gaussian modulated by a sine wave. Okay? So my dilated wavelet is my dilated Gaussian modulated by a sine wave whose frequency has been multiplied by 2 to the minus j. If you look at what's happening in the Fourier domain, you multiply the Fourier transform of your function with the Fourier transform of the wavelet, which corresponds to the Fourier transform, let's say, of the Gaussian translated by the modulation frequencies. That's what you get. Okay? Now, this is a signal centered at this frequency, but its bandwidth is small. So you can write it as a small bandwidth signal modulated by a frequency. This is Fj, which is the component of the frequency here modulated by, convolved with the Gaussian dilated. If you take the modulus, basically you get rid of the modulation frequency, and that's what you get. You get your high frequency component convolved with the Gaussian modulus. Basically, what you will have done by taking the modulus, you take this and you map it back to low frequencies. Almost. Almost. Why? Because whenever this has a 0, the modulus will create a singularity. And therefore, it's a nonlinear operator. You will create some high frequencies besides. You will not create too much high frequencies if your function doesn't vanish. And if you get a complex function, you have much less chance that it's going to vanish. That's why we're going to use here complex wavelets. Okay, so let's get a different intuition of what's happening here. Suppose you have a function which is a sum of sine wave locally, okay? So here I have the Fourier transform is just a sum of few sine waves. Now, if you compute the wavelet transform at 1 octave, okay, basically you are just going to select a sine wave covered by the wavelet dilated by 2 to the j. Now let's take the modulus square. The modulus square is going to be the sum, so you'll have the energy of each of the components there, and then you'll have the sine wave selected by the wavelet, modulus squared. It's going to create interference, and basically it's going to be a combination of the cosine of the difference of frequencies. So what you see suddenly is when you take the modulus, basically you don't know anymore what is the frequency. The only information you have is about interference. You know the differences of frequency. Think of it as the perception of a musical chord. If I give you, for example, a C major, unless you have a perfect pitch, and very few of us have a perfect pitch, you won't be able to know that it's a C major. It may be a C major, E major, D major, you won't know. But you will clearly hear the fact that it's a major chord. And you'll feel about what octave it is in. What does it mean to be a major chord? It means that the first interval is a major third, second interval minus third, and you have a perfect fifth here. So basically, when you hear a chord, you don't hear the precise frequency, you hear frequency intervals. Now that's exactly what's going to happen here, because we are going to get rid of the precise frequency, we'll carry the frequency interval, and we'll know over what octave does it happen. And that's the representation we're going to get, plus the other components that are going to move away. Okay, so let's see how we're going to do that. You make the wavelet transform, okay, and that's the different component of the wavelet transform. Now, the next step, as I said, we're going to take the modulus. So each of these components, now, when you take the modulus, is now mapped to a lower frequency signal, okay? And the basic idea is that we are going to repeat this operation to progressively map all these signals to lower, lower, and lower frequencies. And I'm going to give you a slightly different intuition with a physics analogy. Imagine your function, f here, is the wave function of a particle. So basically describing the state of a particle. Now your particle is in a sphere with a detector at the periphery of the sphere. And within this domain, there are all kinds of other particles. Now this particle is going to move. And when it moves, it may interact with other particles, or it may go directly to the detector, okay? An interaction with another particle is going to create interference term, and it may happen at any time interval between 2 to the minus j minus 1 and 2 to the minus j. And if it happens, you have an interaction which is given by the convolution with a wavelet. Or it may interact at this other time interval, or it may diffuse, in which case, basically, the wave function is just diffused, convolved by a low-pass filter. Think of it like as a Gaussian. So that's one possibility. Now, after the first interaction, it may again interact with any other particle, okay? Or it may diffuse to the detector. So you again going to have a new interaction operator, and so on. And you see that your particle can follow any path, and in fact there is an infinite number of paths corresponding to all the possible interactions, okay? So basically what we're going to do is to iterate on this one-step propagator, which takes this particle. You may have any kind of interaction, first step, any kind of interaction, second step, and so on, corresponding to wavelet convolution modulus, okay? And it defines a path. And we're going to look at what's happening along all possible paths, okay? So I'm going to define here what I call here scattering operator. And the scattering operator basically takes f along all possible paths. Exactly like in quantum physics, where you look at the evolution of your system along all possible paths, and an evolution along a given path is just a series of convolution modulus with different wavelets. The number of steps you are going through is going to be called here the scattering order. It's the number of time you take a convolution modulus and so on. If you think of the norm square of this, if the norm square of f at the beginning is normalized to 1, this is basically the probability to reach the detector through the path P, okay? And you will look at all of these. Okay, let me come back to my signal processing. I've taken the modulus here. And as I said, I'm going to iterate. Oops. I'm going to iterate. So here, I'm going to take this signal and compute again the wavelet transform. A priori, the infinite wavelet transform, all scale. But observe, at high frequencies, I have essentially 0 because I've mapped my signal to lower frequencies. So the most active path will be these ones, okay? And a priori, I may compute all of them, but for the drawing, I will remove the other one. I will keep just these ones. And I will do that for all of them. So for each of them, I'm going to compute the wavelet transform. And again, I'm now going to compute the modulus. So these high-frequency signals are going to be mapped to lower frequency signals again, okay? And now I'm going to repeat again. I take each of these, compute the wavelet transform and modulus. Again, I'm going to have even lower frequency signals. This is the scattering across these different paths. These are the Fourier transform, which gets lower frequency. These are slightly higher frequencies. I repeat it, I get that. Okay, what did I build here? I basically built a neural network, a convolution network, where along each star over there corresponds to a convolution with a wavelet and modulus. After one, it may do a convolution with a wavelet and so on. And you see this kind of network appearing. And at the bottom, this is the output layer, if you wish, of your network. What do you have? You have very low frequency signals. Now, if you let J increase, the scale, the final scale increase, it's like the size of your sphere where you did the scattering. These are going to converge to lower, lower, and lower frequency until it's going to converge to a constant. If you look at this constant, what is it? It's basically going to be the L1 norm, the integral of the series of convolutions. So here, at the end, you'll just get one number. It's not going to be anymore a signal. It's going to be a constant. Okay, let me quickly show what's happening in multiple wavelets, like in 2 dimensions. The only difference is that you don't have one, but multiple wavelets at each scale. And basically, you just repeat the same thing. For each of them, you're going to spread it into, by doing again a wavelet transform modulus. Wavelet transform modulus, you do for all of them. So it gets a mess. The tree is absolutely huge, and it looks a bit hopeless. Okay, to understand why, in fact, it's not hopeless, we're going to look at the property of what we want and what do we want, the metric. Okay? What we want to do at the end is to compare signal. Let's not forget, my goal is to compare signal and to have a distance which is invariant, not only invariant, but which provides me information about deformation. So this is the distance I've built here. And it's basically given by doing the distance for any path P between the response of F and the response of another signal G. I look at the L2 distance. And now I'm going to sum over all paths. So it's the sum over all paths, sum over all position of the distance squared. That's the L2 distance that I have here. Okay, first of all, a simple property to see is that I have a contractive operator. Why do I have a contractive operator here? Because what did we do? First, we did a first wavelet transform in red. The wavelet transform is contractive. Now, at the output of the wavelet transform, I did a second wavelet transform in green. And then the third wavelet. So you iterate over a contractive operator, therefore you have something contractive. Okay? It's an iteration of a contractive operator. Now, the only thing I get is the output here. And therefore, the norm of the output is going to be smaller than the differences of norm between the original signal, just because you iterated over contractive operators. Now, a much more surprising and subtle property is the fact that, in fact, you have a unitary operator. Now, why is that so? Okay, what's happening? I said I was iterating here over a unitary operator. But look, when I iterate, I have the nodes which arrives to the bottom. In some sense, these corresponds to the particle which reached the detector. And then you have all the nodes which are on the side, which is the response of the wavelet transform at the many scale and which didn't go to the low frequency. Here in yellow, you have an infinite number of nodes, whereas here you have much fewer nodes. Okay? Now, what is unitary? If you sum the energy of everything, you get back the energy of the signal. But what I'm only interested in is the energy of this. Now, what you can prove is that when you increase m, namely the scattering order, the energy of all these yellow dots tend to 0. Not each of them independently, but when you sum all of them, the energy goes to 0, and therefore you conserve energy. The energy of your scattering signal is the energy of F. What does it mean? It means that all the particles go to the detector. You have a 0 probability to have a particle which gets stuck inside. Now, there is something important coming as a byproduct. What's happening? The reason why this is happening is because, as I explained, I map each time things in lower frequency. So there is very little energy that is residual in high frequency. What does it imply? It implies that I can completely neglect all these paths. The second thing that comes as a byproduct is the fact that when the scattering order increases, you can verify there is an exponential decay. That means you don't need to iterate this transform many, many times. After 3 or 4 times, basically, the energy is almost 0. that means that in fact you have very few paths that carry the energy. And that's again in analogy with quantum physics, where you have this infinite number of paths, but then you have this Feynman diagram which tells you, well, but out of all these paths, there are very few around the classical path and around other paths where you have a non-zero probability to go through. And that's similarly the same kind of property happening. Okay, now what's happening if I begin to increase J? J is my scale at the bottom. And I said if I increase J, I'm going more or less to converge to a constant. One property again is that the distance is decreasing with J. So if I increase J, I'm going to converge to some number. Okay, I have a decreasing sequence. It's going to converge. It's going to define a distance. So ultimately, I'm going to have a limit distance. My limit distance is contractive and preserves the norm. If I am in the case where I have a compactly supported signal, then everything is simpler. You can do the same kind of trick than in the Fourier transform. You make a periodic extension, and then basically when your scale reaches the size of the support, you get a constant. You get a constant, and what is this constant? This constant for the transform is, as I said, basically the integral or the L1 norm of the sequence of convolution modulus, and so on. And you have a distance which is a discrete L2 distance. It's just a distance defined over all paths. So the important thing here is to think in the Fourier transform, the variable is a frequency. Here the variable is a path, okay? But otherwise, similar property, although here it's very nonlinear, you have a distance which is a Euclidean distance, and you have a conservation of energy. Now, when your function doesn't have a compact support, it gets much more complicated because you don't have that kind of convergence, and the path goes to a continuous path space. But basically, for the applications, we're in that framework. All right, so now let's go back to first property that we want, translation invariance. Okay? If my function is translated, the transform of the translated function is just going to be translated. Why? My transform is just a convolution modulus. If you translate a function, the convolution translates. If you take a modulus, the modulus is going to be translated. So everything translates. However, I said at the bottom, I converge to a constant. So a constant translated is equal to itself. And indeed, you verify then when J goes to infinity, the distance is going to be 0. And if you have a compact support, you don't need to go to infinity. You just stop at the support size. So first thing, I get back my invariance to translation, like in the Fourier domain. But that's not really the core thing. The core thing really is stability to elastic deformations. Now, why do I have a hope to have this stability? Because what we did here is a cascade of the wavelet transform. And the wavelet transform is stable relatively to elastic deformation. And that's the core result, which tells you, if now you have a deformation, now tau depends upon x. So you have a certain deformation given by this elasticity term. If the scale is large, sufficiently large, and you look at the distance is basically going to be proportional to the grad. So basically proportional to the elasticity term. And what you have in front is a log, so the log will be basically neglected. And the norm of f, but the norm of f is not exactly the L2 norm. It's very close to an L2 norm. It's slightly more regularized. It's given in the wavelet domain by this kind of norm. It's a very weak regularity norm. So basically, you get your result up to a log factor. And the proof goes as follows. If you look at the distance between the deformed signal transformed from the original signal transformed, what you'd like is to invert these two operators. If you invert these two operators, then you get this first term, and you get a second term, which is the error when you inverted the two operator. In other words, you get the commutator. And the key issue in all these things is to compute the commutator. And the commutator here is a singular operator, but it is bounded You do the calculations, and that's how you get this type of result. Okay, something which is going to be very important both for classification and also to identify the deformation. What basically you are doing here, you are linearizing the deformation. If I look not at the error with respect to the signal transformed, but I go to the first order, I do a kind of Taylor series, so I take tau plus grad of the deformation. You get an error which is even smaller, which shows by the fact that the error term is appearing at the scale which is much finer. What is this result telling you? Basically, it tells you locally the deformed signal transformed looks like the deformed signal plus a linear term. So locally, the deformation in the transformed space is linear. So there's two consequences. The first one is that we will be able to do classification with linear algorithm. We will be able to do classification with PCA, basically. The second thing is that now you can identify tau. If this is nearly 0, you can set up this equation, and you get a system of equation because for each path you have an equation, and you need to identify tau of x. Now, this, for the one who have been working in these areas, for example, so that means you can estimate optical flow, stereo, and so on. It looks very similar to the type of techniques when people compute optical flow by projecting it on other wavelets. The reason why these, again, techniques didn't work is that to make it work, if the velocity is big, you need to have a very large wavelet. You lose all high frequency. In other words, if you have a small ball moving fast, you don't get it. Here, you have the same kind of result, but this carries the high frequency. So if you have a small ball moving fast, you have the trace of it, and you see the interference created by this small ball that are moving fast, which still exists in the equation. Okay, before moving to the application, let's look at stationary processes. So if you have a stationary processes, then the transformation is also stationary because transformation is a convolution, stationary stays stationary, and modulus stationary stays stationary. If I look at the expected value of the transform, therefore it's not going to depend upon x. In fact, it's not going anymore going to depend upon j because this just makes an averaging. Second property, the variance of your transform is going to decay exponentially as a function of the scattering order. In other words, if you iterate many times of a wavelet transform modulus and so on, you are going to reduce the variance. Why? Take a stationary processes. So I said the convolution is stationary here. The modulus is also stationary. That's what you do. Think of it, for example, as a Gaussian process. The wavelet is complex. So this is a complex function. Therefore, the phase is going to be random and it's going to be anywhere. You take the modulus, you kill the phase. You kill the phase, you kill a source of variability. And therefore, you reduce the variance. You can see the variance reduction is going to be a factor 1 minus pi over 4 if f is Gaussian. So progressively, when you remove variance, you reduce the, when you remove phase, you reduce the variance. So now suddenly you have a distance. You have a distance of a stationary processes. Basically, it's going to be the distance between the expected value of the transform for one process minus the expected value for the transform of another process, sum over all paths. So you can verify this is finite. But what is interesting, as I said, is that the variance is getting reduced. What does that mean? It means that with a single realization, if I'm in a good case, and all textures we've encountered are basically, in the case of images in databases, were good cases, with a single realization, we'll look at the distance, and it's going to be very close to the expected value distance. Let me give you a picture of that. Take a white noise. It's basically living everywhere on the sphere. Or another Gaussian process, it may, or not Gaussian processes. That's another process. What I'm saying here is that these two processes are going to be mapped in the neighborhood of a point on my transform domain. And it's going to be mapped in a very small ball, and the ball is going to decay to 0. And what I'm going to show is that the distance between these two things are big enough so that I can discriminate them very easily. So to discriminate two realizations of f and g by doing the distance here, it's hopeless. Take the distance between two realizations of a white noise, you basically get garbage, okay? It's big, it's the energy of them. Now, in the transform domain, the distance we'll just have to make a Euclidean distance, and we'll get our metric. Okay, computational complexity before showing the results. Signal of size n, because each time basically I'm lower and lower frequency, I can subsample my output signal by a factor to the j. If I go to the depth j, I showed you that most of the paths basically carry no energy. So the number of paths that I'm going to keep is smaller than a certain m, the order, basically m is going to be 3, so very small. The number of paths, if I have k wavelet, is going to be proportional to k to the power m, j to the power m. The maximum depth I can go to is log n. So basically the number of coefficients, because each path at the bottom corresponds to one coefficient, the signal is constant at the bottom, is going to be log n to the power m. So my representation is much smaller than the original signal. Not surprising, because I've created invariance. I've lost information. So it's not surprising I get something which is smaller. I did a dimensionality reduction. Basically, m equals 3, k equals 4, computations O of n. Okay, the results, the way I'm going to show them first, I'm going to show, so at the bottom of the tree, you have in blue here, just this is the average of the signal. The red output are basically the average of the modulus of the wavelet transform. So these are the L1 norm of wavelet coefficients. Green, these are second order coefficients because they went through 2 steps. Yellow, third order. I'm going to reorder everything so that you'll see average, first order, second order, third order, and so on. Here's what you get for a simple signal like that. Not very intuitive. This is the average, amplitude of the wavelet coefficient, which reflects you where the frequencies. Second order coefficient, third, and then you see nearly 0. That's the exponential decays. When the order gets big, you basically have nothing left. That's why we keep basically the first 3 orders. Gaussian white noise. These are 2 white noise. This is Gaussian, this is Bernoulli. You compute the Fourier transform, they are identical, flat. Okay, power spectrum is a constant. You go here, these are the transform. The variability is very small, in fact. It varies because that's the value of the coefficients. If you look at this and this, they are different, okay? So the distance will just be this minus this, squared. And you sum over. Here the axis corresponds to a path, okay? It's just the index of a path. It's a path along my tree here. Okay, classification. So this is the work of Johan Brunat, who is a PhD student at École Polytechnique. Basically, the idea is the following. When you have to do classification, think of it as digit classification. You have deformations, clearly, when you write a 2 or a 7 or 1. But some deformation will take you very quickly out of the class. Some deformation will keep you inside the class. Think of a 7. If I make the lower branch longer, it's still a 7. The upper branch longer, it's still a 7. But if I take the upper branch and I begin to rotate it, I'm going to get a 1. Okay? Some deformation are okay, some are not okay. Okay? But the good thing is that my deformation have been linearized. So I'm going to look at the deformation and basically say, as long as I have deformation that are within the class, it's okay. But deformation which takes me out of the class, it's not okay. So I'm going basically to define a distance which is not, so my class is sent somewhere in my manifold by my transform. I have the mean of all the elements of the class. And I'm going to say, well, along this direction, I had a lot of deformation, so it's okay. So the distance between a signal and the class will be defined as just the distance between the transformed signal and the affine space that I will have selected going through the average. And the affine space basically carries all the large variability components which are okay because it keeps me in the class, and I only want to measure the component orthogonal to this affine space, okay? And when I have a texture, this affine space basically carries high variability component of my texture within the transform space. So here I'm getting closer, but I'm sorry, it's the very primitive way to do independent component analysis, namely principal component analysis. And that's what we're going to do because basically we linearize the problem. Important thing, the learning is linear in the number of training coefficients. So for each class, you take each element of the class and you transform it. You take the average of all of them. You compute the covariance of the transform coefficients, okay? So now you have the average and the covariance for each class. What you want is to find the space which, in some sense, best approximates the elements within the class, which will give me the direction of variabilities. For doing that, we know the simple way, an optimal way, is to do a PCA, namely you diagonalize the covariance, you get the m eigenvectors corresponding to the largest eigenvalue, and you get your space. Classification. The classification is going to be proportional to log n to the power m multiplied by the number of class. So you have a signal, you transform the signal, and for each class k, you are going to look at the distance between the transformed signal and its projection on this predefined affine space calculated with the PCA. The problem is you don't know what should be the right dimension for m. What is the right dimension? The right dimension is, m in some sense is the number of independent deformations which maintains you within the class. Now, if you think of a 1 is not very much deformed. But if you take an 8, there are plenty of deformation which remains an 8. Therefore, m should depend upon the class. And how do you make m depend upon the class? Where you let m vary, and you basically you do a linear model selection. Namely, you take the m which minimize the distance penalized by the dimension m, where lambda is the penalization factor. So if you find the optimal over m and over k, it will give you the best class. It's the class which minimizes the error given the penalization over the dimension of the space. So this learning algorithm has two parameters. One is lambda, two is j. What is the depth on which you want to work? So we began with the most standard databases used worldwide for classification of digits, handwritten digit, which is called MNIST, that was defined by Lequin about 15 years ago. So you have a database of digits, and you have all the result of all the algorithms of the world, basically, doing that kind of thing. That's the training size. You may have, so you have 10 class, 10 digits, okay? And 100 training elements, that means you have only 10 elements per class, up to 60,000 training elements. Yeah. These are the results with a support vector machine. The result for a support vector machine, you go from 28% to basically 1.4%. That's the state of the art with a deep neural network, 6% to 0.64%. The learning time for that kind of thing is about 24 hours on computer cluster. Here that goes on a laptop of Mac. We basically have the best result right now, state of the art, for until 5,000, it goes to 1.3%. And when you go to 60,000, we get slightly worse than here. These are the results. If you look compared to SVM, support vector machine with any kind of standard kernel, these are the best kernels used. Not only it does better, if you look in the terms of number of variable, you see that we classify with much less variable, in fact. The number of variable in our case is the dimension of the space. It's 160 as opposed as 2,000 for a support vector machine, which is the number of support vectors. And it goes much, much faster. This is an algorithm in this number cube. Okay, and whereas here you have a linear algorithm. I'll skip over that. I'll show textures. This is a database of texture that was put together by Mallat. You have textures which are illuminated along different directions. Okay? So this is one texture class, second texture, third, fourth. They don't look so much alike within a class because of variation of illumination. So that's again a standard database, 61 class, 46 element per class, training set 46. Result of Mallat from Berkeley, so these are based on 3D textons which were adjusted to reflect the property of textures, 5.35%. Zisserman was holding state-of-the-art Markov random field, Gibbs sampler, very long algorithms. And we go, boom, 0.4%. So there is an improvement by a factor 6. And the speed of the algorithm is incomparable, again, because it is basically linear. The only property we've really imposed is basically stability to deformations. Okay, very quickly, what's happening? How do you generalize? Look at this bar, this one. If I ask you, do they have the same orientation? Very hard to tell. If I put them together, very easy. It's like in the case of audition. We are very bad to measure frequency, but we are very good at measuring intervals. Basically, invariance to any kind of groups like that, you do it the same. You take your wavelet, you transform it by the group, you get a whole family. So think of it now as rotation. Take the wavelet, you rotate it. So you get all the rotated wavelets. You dilate all the rotated wavelets, and you get a wavelet transform for all rotations, angle, and all scale. Now, if you take your signal, you rotate it, and you compute the wavelet transform, you get a rotated wavelet transform, but now the channel of rotation has changed. Basically, you get a translation along the rotation angle and a global rotation along space. Basically, if you want an invariant to rotation transform, now you need to, basically, something invariant to rotation is like a translation, but along angles. So you basically do the same thing. You take your wavelet transform, but now you apply the transform along the angles, so just along the angles. It's like a transform within layer of your network. Take the modulus, reapply, apply along angles, and so on. Okay, so just to illustrate that basically you can do any kind of these groups, you just apply the same transform along the group parameter. Okay, the conclusion. So, I mean, for me, the first conclusion is I was very surprised by the property of these operators. I was very surprised because, like many of us, and I've been discussing with a number of mathematicians, there was this belief that basically, if you want translation invariance, full translation invariance, either you get rid of the high frequency or you are dead in terms of stability to elastic deformation. So there is a lot of interesting issue now in terms of mathematics, in terms of characterization of stationary processes, which are the ones that can be characterized or not. Again, what I showed is that textures which are not discriminated by Fourier transform, and basically all textures of images are not discriminated by Fourier transform because they all have the same power spectrum, like decays like 1 over omega. In this case, we can discriminate them. Some texture can be discriminated by Fourier and not by this kind of thing. There are all kinds of issues on the attractor. In terms of applications, so I'm at the stage where I have the impression that everything can be solved by that. Like each time you get something new and then you realize the world is not so simple. But everything can be solved by that. So we worked on audio. Very interesting. Audio, when you do the transform, I told you about first order coefficient. What are the second order coefficients? They get you the attack. It was very surprised when we take an audio signal, we get rid of all the wavelet coefficient, all the first order. We just keep the second order coefficient, which basically gets you something very sensitive to attack, and we discriminate instrument much better than if we keep the wavelet coefficient. So when you go to higher order, you get very interesting property about basically timbre, the timbre. There are all kinds of interesting things, estimation of motion and so on. Neural net, basically what you're building here is a neural net. So it's maybe a mathematical basis to understand at least certain classes of neural net. Biologically, there are also very interesting things because we know that wavelets are around in the cochlea, in the visual cortex. But what nobody knows is what's happening afterwards. What are the nonlinearities? On the other hand, what we know is properties of perception, the fact that we are invariant and so on. Now there is a mathematical question. Is it possible to do it differently? In other words, is it possible to get stability to deformation, which we need for perception, and do a completely different strategy? If it's not possible, then there may be a chance that biology is implemented that way. And I'm still under the impression that it's very hard to do around, but there is no proof here. And then, of course, relation with quantum physics, which is interesting, but that's another topic. All right, thanks very much. Thank you. I'm okay.